Yes. Let us have detailed discussion about the crash course error analysis. Usually error analysis start with measurement. Measurement is something comparison. Suppose I want to measure length of my height, I will compare my height with the known length. Suppose if I have meter scale, I can compare my length with the meter scale, how many meters I will get, or I will get compare with the centimeters. So the comparison of a quantity with a similar standard quantity is called measurement. Now let us measure length of a rod here. And this rod, to measure the length of this rod, I have to use any known length, that is a centimeter scale here. If I want to compare this with this one, I am getting length of this one 4 centimeters point something. And how many or how much, up to what centimeters I can measure the length of the rod accurately here? Up to 4 it is certain quantity, but after 4 how much I don't know. So there is some measurement even after 4 centimeters that is not known here, because we do not have the digits to measure or proceedings to get the meter scale. Suppose if I take the millimeter scale, now I have very confident to measure this up to 4.2 centimeter. But after 4.2 centimeters also, there is still certain edge. It is more than 4.2 and less than 4.3. Here the conclusion is up to 4.2 centimeters it is certain measurement, and after 4.2 I have to guess. It might be 4.23, it might be 4.26, it might be 4.28. So 4.2, 2 digits are certain here, and after 4.2, one more digit will be added based on our guess, that will be uncertain. So the measurement of this can be written as 4.23 or 4.24 or 4.26. Suppose if I want to measure this one with even more accuracy scale, even more resolution scale, that we can measure here. Suppose if I take even more, measurement can be taken with another way, like suppose screw gauge or vernier calipers, even micrometer, microscopic meter. So let me take, to get the more closer measurement, vernier calipers. In vernier calipers, 4.23 centimeters can be measured accurately, and even after 4.23 there will be uncertainty. So here the minimum measurement I can take with this one is the 0.01 centimeters accuracy. So the least count of this one is 0.01 centimeters. Suppose if I take another instrument, let us say, to get furthermore closer to the measurement, I can take screw gauge, and in screw gauge we can measure up to 0.001 centimeter accuracy. That means 4.234 centimeters. Suppose if I want even more closer accuracy, I need to take further minute measurement, that is microscopic instrument, to get the length of this one. Here if you observe, this measurement indicates 4.234 indicates 4 significant figures where we have the certainty in the measurement. And to get furthermore closeness, we can use microscope. Microscope can measure up to 4.2342 centimeter, even more accuracy. So maximum possible uncertainty here is 0.0001 centimeters. So like this, we can conclude here the least count is the minimum measurement or maximum uncertainty, maximum possible error for any kind of instruments. And the second thing, the measured value, whichever it is available here, this indicates some digits are there to represent the measurement, and those digits are called significant figures. And significant figures definition can be understood in this way: the number of figures which are correct and one uncertain digit, the first uncertain digit, all together can give us the measurement of any quantity, and that we call here significant figure. And to estimate the number of significant figures, right from spectroscopy, we have developed one shortcut technique. And for that, first we will take any quantity we have to estimate A, B, C. So first we will check whether the given number or given quantity is decimal number or not. Suppose if it is not a decimal number, then we will be getting one non-zero digit, another one zeros between the non-zero digits. So non-zero digits are treated as A, zeros between non-zero, zeros between non-zeros, that is sandwich zero, it is treated as B. And the formula for this one is A plus B only, C is not applicable here. Suppose if you have the given number as the decimal number, then you have as usual like earlier non-zero digits as A and zero between non-zero digits as B, and one more trailing zeros in the case of decimal number. Trailing zeros means rightmost zeros after last non-zero, whatever the zeros available, even if it is after decimal or before decimal, after the last non-zero digit, how many zeros are there, those zeros are called trailing zeros, and we should add them. I hope you got it. If it is not a decimal number, only A and B. If it is a decimal number, A, B and C altogether we should count. Let us try to understand with a good example here. Let me take a measured value here, 0.5000 kilograms. And how many significant digits are there? So as per our technique, we should estimate how many number of non-zeros. A equal to 1. Are there any zeros between non-zero? No, only one non-zero is there, so B is not possible. Is it a decimal number or not? Yes, it is a decimal number. And how many trailing zeros are there? 1, 2, 3. Total 3 trailing zeros are there. So our significant figure formula is A plus B plus C, and here A equal to 1 plus B equal to 0 plus C equal to 3. Altogether 1 plus 0 plus 3 equal to 4. So 4 is answer for this one. Let us try to understand more with one more example. 6,000 meters. Earlier it was 0.5000, it was decimal number. Now it is non-decimal number. So for non-decimal number, A and B only will be there. A equal to 1 and B, when there is one non-zero digit and 0 between non-zero is not possible. So for this B 0, and it is not a decimal number, so C is always treated as not applicable or 0 simply. So significant figures are 1 plus 0 equal to 1. You might be wondering here, 0.5000 is getting 4 significant figure, whereas 6,000 is only 1 significant figure, because significant figure is related with least count of the instrument, resolution of the instrument. So be careful. Now let me take another one, 0.0080. In this case, A equal to 1 and there is no sandwich 0, so B equal to 0. As it is a given number is a decimal, so C will be there. Trailing zeros, that means rightmost zeros. How many are there after non-zero? Only 1, so C equal to 1. So altogether I will be having 1 plus 0 plus 1, that equal to 2. Let us take one more. Suppose if you are given in scientific notation, 1.124 times 10 power minus 3, here you should ignore this scientific part, 10 raised to power. Only consider this 1.124, and in this 1.124 it is a decimal number, and here fortunately we have all 4 digits are non-zeros, so A equal to 4. There are no zeros, so no question of the B and C. Simply the significant figure you will be getting only 4. Suppose if you get a question like this, let us say concept connector 1 in your competitive exam, count number of significant figures in 3.0800. So such kind of the questions, always I told you, you should focus on whether it is decimal number or not. Just check that one. It is decimal or not. It is a decimal number, so there will be A. How many digits non-zero? A equal to 2 plus how many zeros between non-zero? Only 1. How many trailing zeros? Because it is a decimal, how many trailing zeros? 2. So total 5, and 5 will be your answer. Suppose if you are given another question something like this, 0.00418, it is a decimal number, and check how many non-zeros. 1, 2, 3, 3 plus how many zeros are between non-zeros, sandwich zeros, no sandwich zeros, 0. How many trailing zeros? No trailing zeros. So the answer is 3. This much simple. Let me take another question here. And 3500, is it a decimal number or not? Once check it, it is not a decimal number. And how many non-zeros? Only 2. How many zeros between non-zero? No zeros between non-zero. And how many trailing zeros? Yes, there are trailing zeros, but it is not a decimal number, so we should not consider this. The answer is only 2. So this is the way to handle significant figures. Let me continue with a couple of more questions like this. Count total number of significant figures in 300.00. Here, how many non-zeros? A equal to 1. How many zeros between non-zero? No zeros between non-zero. Is it a decimal number? Yes, it is a decimal number. How many trailing zeros? Here, the misconception is most of the students will consider only after decimal zeros. You should consider always after the last non-zero, how many digits are there? All are trailing zeros. So how many are here? 1, 2, 3, 4. So total here is 5, and 5 will be your answer. Let me consider another question. Count total number of significant figures in 5.003020. Here how many non-zeros? 1, 2, 3. 3. How many zeros between non-zero? These 2 zeros, they have left side non-zero, right side non-zero, so they are considerable. And this 0 is having left and right, 2 sides non-zero. So how many zeros between non-zero? Sandwich zeros. 1, 2, 3. This is 3. Plus, is it a decimal number? Yes, it is a decimal number, and you should consider trailing zeros. How many rightmost zeros are there? 1. So total 7. 7 will be your answer. Let us consider one more. Count total number of significant figures in 6.020 into 10 power 23. I told you already, scientific notation part you should not consider, and you are left with only 6.020. How many non-zeros? 1, 2. Super. Next, how many zeros between non-zero? Only 1. 1. Is it a decimal number? Yes, it is a decimal number. As it is a decimal number, we can consider the trailing zeros. Only 1. 2 plus 1 plus 1, it is 4. So this is the way to handle, and let us have last question in this area. Count total number of significant figures in 1.60 into 10 power minus 19. Here A value 2, B value 0, C value 1, total 3. So this is the way to handle significant figures. Now let us have a genuine thought-provoking situation here. Suppose I want to measure the length of the string as well as the size of the bob, which are the part of the simple pendulum, and the system is suspended from the ceiling. Let us take this ceiling here, and there is a string, and for this string it is connected here bob, and I have length is given as 75.4 centimeters, and the radius of the bob, this is the point O, let us say, and this is the point A, let us say. I want to find out AO distance here. What is AO distance? AO is L plus R. If I consider this is L and this is R, I want AO equal to L plus R. I want to add just these measurements. One addend is 75.4, another addend is 2.53 centimeters. Let us do that one mathematically. So I have L plus R, and L plus R value, first one is 75.4 centimeters, second one is 2.53 centimeters. I want to add this one. So mathematically we will add something like this. 75 plus 2 is 77, 4 plus 5 9, but 3 plus what is there here? Here, I don't know which number is available. Mathematically, we consider this as 0, and 0 plus 3, 3 we will put here. But scientifically, as this value is not known in the sense, at the time of measurement, the instrument which was used to measure the length of the string has no accuracy beyond that level. That is why we could not measure this point. And as I don't know this one, even here also I don't know. I can measure or I can add up to 1 decimal only, accurately. Up to 1 decimal point only I can measure accurately. Beyond that I don't have accuracy. This one is not accurate. And this is the practical challenge we have come across while dealing with the operations of the measured values. So to avoid this, scientists proposed a technique, and that technique is rewriting the result with appropriate number of significant figures. And for that, how to rewrite the result, what are the rules behind this, and everyone should follow that only. Suppose if your operation is addition or subtraction, you have to report or rewrite the result according to least decimal. What is this one? Least decimal. Suppose your operation is either multiplication or division, even powers, you will be rewrite the result according to least significant figure. It is very simple. If it is addition or subtraction, go for the least decimal. If it is multiplication or division, go for the least significant figure. Simple. This is the fundamental rule in rounding off. What is rounding off here? Rewriting the result according to appropriate significant figures. According to appropriate significant figures. Now, next, let us check how to do that one with an example. 5.8 plus 0.125. Suppose I want to add this 5.8 with 0.125. While adding this one, I can add this from right side. If I want to add, I have 5 to 8 plus 1, 9, 5 plus 0, 5. But here I don't know which value is available. Here I don't know. As I don't know here, I can add this up to accurately up to how many decimals? Only 1 decimal. So to make it as a rule, let us try to understand here. We have to rewrite this result. Before rewriting this result, as this is the addition operation, how many decimals in the first addend? Only 1 decimal. And how many decimals in the second addend? Only 3 decimals. So which of them is least? 1 is least. So our result must be rewritten. Our result must be rewritten to that 1 decimal part, and that reporting or rewriting process is called rounding off. So rounding off definition is the process of rewriting or reporting the result according to appropriate number of significant figures or according to most accuracy is rounding off. And let us discuss about rounding off techniques now. Rounding off is very simple. Again, we have developed a technique here from spectroscopy, and that development is, I will let you know here. Again, if the operation is addition or subtraction, it is least decimal. Multiplication and division, it is the least significant figure. This one already just reminder I am saying now. Let us take a good example here. Suppose there is a result 47.862 and I want to rounding off to this one to 4 significant figures or 3 significant figures or 2 decimal or 1 decimal. So for that, to apply this technique, we have developed a vocabulary to apply the technique. That vocabulary, we have to remove the digits here. To increase the significant figures, direct scientific notation. To decrease the significant figure, we have to remove the digits. So before removing, we need to understand what is the digit which we are going to remove. So that is named as DTR. D for digit, T for to be, R for removed. And the digit which is just before to DTR, that is previous to DTR, is called as PD, P for preceding, D for digit. So you must be aware of the language DTR and PD. These two things we must know. And the technique here is, suppose if the DTR is greater than 5 and PD must be increased by 1. If the DTR is less than 5, PD remain same. If the DTR equal to 5 and followed by non-zero, after 5 something is there, some number is there other than 0, then at that time blindly you can say PD equal to PD plus 1. Suppose if DTR equal to 5 and followed by nothing or 0, in that case you must be careful, and here the checking point is PD. If the PD is odd number, PD must be increased by 1. If the PD is even number, PD remain same. Yes, so this is the technique. When DTR greater than 5, PD will be improved by 1. When DTR is less than 5, PD remains same. When DTR equal to 5 and followed by any non-zero, PD becomes or raised by 1. If DTR equal to 5 and followed by nothing, here again we need to check PD. If PD is the odd number, then PD becomes PD plus 1. If PD is even number, PD remain same. In which case we will get PD remain same? One case is DTR less than 5, another case DTR equal to 5 and followed by nothing and PD is even number. Something like this, 2, 5, 4, 5, 6, 5, 8, 5. In all these cases, PD remain same. So this is the idea. Let us try to discuss one example here. There is a number given or a result, let us assume it is a result, 16468. Round off to 3 significant figures. How many significant figures are here in this number? 5. And up to how many significant figures we need to remove or we need to round it off? 3. So how many digits we need to remove? 2 digits we need to remove. So for that I told you already, we need to be very clear about the vocabulary as well as the technique. So in this, I need to remove 2 digits. And after removing the digits, what to do? If it is a decimal number, just remove. If it is not a decimal digit, remove and replace with 0. And given thing is not a decimal number. So if I remove any digit here, I need to replace that with 0. Okay, now here what is 8? DTR. And how is the DTR? Greater than 5. When DTR is greater than 5, what is the rule? PD equal to PD plus 1. So what is PD here? 6. So 6 will become 7. As it is not a non-decimal digit, so it is must be replaced by 0. So now 68 will become 70. So it is 16470. Now how many digits are here? Significant digits? 4. But how many do we want? 3. So I need to remove one more digit. So which is DTR here? The new DTR is 7. And again, how is the DTR? DTR greater than 5. Again the technique, if DTR is greater than 5, what to do? PD will be increased by 1. Now what is PD here? 4. And 4 will become 5. 7 will be replaced by 0. So I will get 16500. And even if you compare this one with this one, they are approximately equal. 16,468 is rounded off to 16,500. Even you need to cross check it finally. So this is the idea. Let us try to check a question from NEET 2020. Considering of the significant figures, what is the value of 9.99 meters minus 0.0099 meters? It is actually a simple subtraction. A simple subtraction. 9.99 and 0.0099. After subtraction, I will be getting 9.9801. And I have the answer also here. 9.9801. So most of the students will fix this one because it is just subtraction. But if you apply the rule here, if you apply the process, so 1 is the DTR, it is less than 5. So PD remains same. Again 0 is the DTR is less than 5. So again PD remains same. So 9.98. You may get this answer. But here if you observe, no need to do all these things actually. Here, what is the given addend? 9.99. Okay. and another thing 0.0099. In case of addition or subtraction, what is our working rule? The result should be having least decimal. How many decimals are here? 2 decimals. How many decimals are here? 4 decimals. So answer should be having how many decimals? Least of these 2 decimals. How many options do we have with 2 decimals? Only one option, and that is our answer. Even no need to calculate this also. All your competitive exams are going to check your smart thinking, check your application skill, whether you are applying that rule or not here. Now, let me come to another question. The area of square is 5.29 meters square. The area of 7 such squares considering the significant figure is. Options are given like this. Here it looks like one square area is 5.29. Yes, one square area. And how many squares are there like that? 7. So usually how we think here, it is multiplication. In multiplication, how should be the answer? Least significant figure. But here, technically, this is the measured value and this is not the measured value. So we should not use that technique. Actually, there are 7 squares, 1, 2, 3, 4, 5, 6, 7 and so on, right? There are 7 squares. To get the total area, I need to add them. Yes, so it is actually which operation? Addition operation. So 5.29, how many times I should add like this? 7 times. So the result will be having, which operation it is? It is actually addition operation. In addition operation, which is the rule? The result should be reported with least decimal. So how many decimals are here? 2. How many decimals are here? 2. All are having same number of decimals. So result also will be having the same number of decimal. How many options are there with 2 decimal? Only one option, and that is going to be your answer. So my dear students, I hope you understood the first thing as the what is the measurement, least count, and also significant figures, as well as the rounding off. We will be having one more session on error analysis. Okay, thank you. Right, now let us discuss about the core concept of the error analysis. Usually error analysis start with the accuracy, precision and least count. These are the 3 pillars of the error analysis. Now, accuracy and precision. What is meant by accuracy? Accuracy is nearness to the true value. Precision is nearness, relative nearness between measured values. Accuracy is the nearness between measured value with true value. But precision is the nearness between measured values. This is the main difference here. Accuracy is this is nearness to measured value with true value, whereas precision is nearness between measured values. Simple, nearness between measured values. Let us try to understand this with an example, shooting. Now, least count. Least count is minimum measurable or minimum value with that instrument you can measure is called least count. Suppose if you take example of the millimeter marking scale, the minimum measurement you can take is 1 mm. That is the least count. So least count is the minimum measurement or maximum probability uncertainty. This is the idea. Suppose in exam, usually in competitive exams, instruments might not be mentioned sometimes. At that time, how to get the least count? How to get the maximum possible error? Least count is same as the maximum possible error. Remember this. Suppose if the error is not given, you should take least count as the error. Suppose if the error is given, that will be your least count. Now suppose measurement only given, then how to handle? Suppose if the measurement is 2.890, and always keep in mind the least count is rightmost digit you keep 1. This rightmost digit you keep 1, remaining all digits you keep 0. That is, in measured value, what is the least value? It will start with 0.001. Suppose if I give something like this, 0.005 kilograms, take this one, keep 1, remaining all zeros, so that will be 0.001 kilograms. Suppose if I give you 15.01, even in this case also, rightmost digit as 1, remaining all zeros, so 0.01 centimeter. Suppose if the measured value is 327.92 millimeters, here the least count is 0.01 mm. Be careful with the units also, units must match. So this is the idea. Last one, if I give you 1111.111 millimeter, the least count is last rightmost digit keep 1, remaining all 0. So 0.001 mm is least count for this one. So this is the idea how to get the least count from the measured value. Let us discuss about accuracy and precision with this example. Shooting. Suppose you are trying to shoot here. Here the spot is very near to, this is actually true value. What is this one? True value. And it is very near. It is very near. It is very near. It is very near. So all are very near. So it is accurate. Suppose here you may be given like this. They are not accurate, but they are very near to each other. So it is precision. Precision indicates the closeness between the measured values. Accuracy indicates closeness with true value. And what is our intervention here? Let us say how will be the questions and how to handle. It is general definition, accuracy and precision. And here very important thing is high precision doesn't mean high accuracy. Be careful here. The instrument might be high precision, but sometimes it may not be accurate. Now let us understand this with an example. There is an experiment conducted. The length of the straight line is measured a few times by an observer, and the following are the results of these measurements. And actual length is 3.785. 3.785. If you take an instrument which can give you whose least count is 0.1 centimeter, so the values will be 3 point something only, 3.7, 3.6, 3.5 like this. If you have instrument with a 0.01 least count, you may be given 3.78, 3.76 like this. So here be careful when the measurements are given to compare with the true value, always consider according to the least count. Suppose, let me give the first set of observation. In this, the least count of these measurements are 0.1 centimeters. So when compared to the true value, you must compare with 3.7 only, not 85. So when compared to the 3.7, 3.8, 3.9, 3.7. Here if you observe, measurements are near to true value. Because least count 0.1 only, so 0.1 difference only. 3.8 is 0.1 difference, 3.9 is 0.2 difference. Now, but they are not near to each other. The measurements are not near to each other. So I can say here accurate but not precise. Suppose let me take another set of observations observed by another observer with a different instrument here. And here the least count of this one is more accurate. Now if you observe, the values are 3.478, 479, 478, 478, 479. All measurements are near to each other. But the true value is 3.785. So once observe that they are far away from the true value. So here the measurements are not near to true value, but they are near to each other. So we can say it is not accurate but precise, or precise but not accurate. Let me consider another set of observations. Third set of observation, 3.55, 3.65, 3.45, 3.35. All are not near and not near to true value, not near to each other. So here I can say neither precise nor accurate. Now similarly, let me take another set of the observations. All are near to each other and all are near to the true value. So that is why it is precise as well as accurate, and this is the conclusion. First set accurate but not precise, and not accurate, not precise, and here neither accurate nor precise. This is precise. Now accurate as well as the precise. So this is the summary of. So the questions might be given like this even in matching kind of the questions. So my dear students, I hope you understood this one. Now types of errors. We are coming to the core syllabus of the error analysis. Types of the errors. We have absolute error, relative error, and percentage error. These are the three major errors, and our numericals, propagation of errors, everything is based on these only. So my dear students, try to focus more from now onwards. It is core area. Usually error means what? Error is deviation from the actual value, or the difference between true value and actual value, I mean measured value and actual value. I can write like this: measured value minus actual value, and here it may be positive or it may be negative. Suppose the true length of the body is 2.5 centimeters. If your measured value is 2.7, in this case measured minus true, 2.7 minus 2.5, your error is positive. Suppose if your measured value is 2.2 centimeters, in this case measured minus true as a error, in this case it is minus 0.3. So error may be positive or may be negative. Suppose if I take average of these two, one is positive, one is negative, I may get zero error. Even though there is error, I may get zero average error. So to avoid this, we have introduced another kind of the error, that is absolute error. We must be very much interested in the deviation only, not with more or less, not with plus or minus. So that is why absolute errors are introduced here, and the difference in the magnitude of the measured value, magnitude of the difference, or magnitude of the difference only. Very simple. Suppose if the true value is not given, what to do? Take average of the all measured readings if the true value is not given. If true value is given, it is okay. If it is not given, you should take average of the measured values. And this average of the measured values and difference between each, A1 minus A bar, A2 minus A bar, A3 minus A bar, all the differences are absolute errors here. These are the errors. From this we will get absolute error by taking here modulus. Okay, so this will be your absolute error. Suppose if you have more than one observation, let us say 2 or 3 or 4 or 5 observations, to understand the effective error, we must take the average of the absolute errors, and that is named as mean absolute error. Always this mean absolute error only will be considered as the error in general language, that is absolute error. So in our three types of error, this is the first one, mean absolute error is absolute error. Now, any measured quantity is recorded something like this, and here this means that if we make a single measurement, then the result of measurement will be between A minus delta A or A plus delta A only. The range is this one. Now, relative error. The comparison between absolute error with true value is called relative error or fractional error. Only comparison. Comparison means in mathematics a ratio. The mean absolute error is compared with true value, that is your relative error or fraction error. And next thing will be percentage error. This relative error is normalized or expressed with reference to the 100 is called as the percentage error. They are very simple. Now, let us try to understand. The period of oscillation of a simple pendulum in an experiment is recorded as 2.63 seconds, 2.56 seconds, 2.42 seconds, 2.71 seconds, 2.80 seconds. And now we need to find out here mean time period, that is true value, and absolute error in each observation, and percentage error. To calculate the percentage error, we need to estimate mean absolute error. Yes. Now, let us go one by one. Mean time period. Mean time period means what? Average. Average means what? Sum of the quantities by number of the quantities. So, 2.63, 2.56, 2.42, 2.71, 2.80 divided by 5. I will get here 13.12 by 5. And dear students, here, don't do this direct division. Instead of this, you can do here 10 by 2. And this 2 can be taken to the numerator and become multiplication. So what do you get here? 13.12 into 2 is 13.12 times 2 is 13 times is 26. 0.12 2 times is 24. Yes, you will be getting 26.24. That is your, and divided by 10 is there. So you will be getting 2.62 only we write, not 4, because it is simple addition of the measurements, in addition least decimal, accurate up to only second decimal. So that is why even though you get 2.624 here, we write only this 2.624 is rounded off to, this 4 is DTR, DTR is less than 5, we will write 2.62 only, and that is why you will be getting your value as 2.62 seconds. So that is mean time period or average, right? And let us continue with the rest of the question. Just now we got true value or mean time period as 2.62 seconds. And what is the next? Absolute error in each observation. What is the first observation here? 2.63 measured value. What is true value? It is not given, so average time period must be taken as a true value, and the difference between them, 2.63 minus 2.62. That is the, even we are taking absolute, that is why the difference here, deviation is here only 0.01. And even in the second case, even third case, even fourth case, even fifth case, all are absolute errors, so all must be taken only positive. And next thing, you must take percentage error. So for percentage error, the comparison of mean absolute error with true value. True value we know already. And mean absolute error, we should take the average of the all absolute errors. So sum of the quantities by number of the quantities, that is 0.01, 0.06, 0.20, 0.09, 0.18 divided by 5. Again we will be getting this one as 0.11, and that is compared with the true value 2.62 into 100. So the simplification of this one will be 4.2 percentage. So this will be your percentage error, third question. So my dear students, I hope you have understood how to deal with this kind of the questions. Now, next, errors in a repeated measurement. Suppose in repeated measurement, the errors will be in two ways. One way will be human error, another way will be instrumental error. This is human error by carelessness, or while taking the measurement you might be looking at different direction. But experimental errors or instrumental errors are due to the fault in the instrument. And second, to estimate the error in a proper way, there is a mathematical technique by Gaussian distribution curve. It is usually, the error will be the number of, if you take more number of measurements here, the main error will be, peak will be like this. It will be arranged in this way, the quantity. Such a curve which represents, this is the Gaussian curve. And mean value. Suppose if you have more than one observation, x1, x2, x3 and so on, then the mean value is given by sum of the quantities by number of the quantities. Or simply I can say here, this mean value is always inversely proportional to number of observations. And standard deviation, how the deviation is occurring. To estimate that, we have a quantity is framed for that purpose, that is standard deviation is square root of 1 by n minus 1 sum of xi minus x average. Xi is the each observation, x average is the mean value. Just now we have found out this x average. Now, and another is there, that is standard error in the mean. That is very, very important, and keep in, and this is very, very important. And standard error is alpha is sigma by root n. Here alpha is inversely proportional to root n. Yes. Now to understand this practically or with application point of view in the competitive exam, there is a question for you. When there are 100 readings, the standard error is E. If that it takes 400 readings, what will be the error? Just now we understood that there is a relation between, or there is inverse proportion between standard error and number of observations. Initial number of observations are given as N100 and standard error is E. Suppose if the readings are 400, then that is N2 is 400, then alpha 2 will be how much? So alpha is inversely proportional to N. I can write alpha 2 by alpha 1 as N1 square root of N1 by N2. Simple idea. And from this, by substitution, N1 is 100 here and N2 is 400 here. Just with a simple simplification, I will be getting 10 by 20, which is E by 2. So this is final answer for this numerical. So this is the way to handle such kind of the questions. Now, random error. Random error, just now we had a discussion in the case of random error in Gaussian distribution curve, and the mathematical part is that is always inversely proportional to n. So here for this I can write x2 by x1 equal to n1 by n2. The comparison, I mean proportion questions only possible in this case. There is a question. Numerical application, once try this one. Here the data is given as when 10 observations are taken, random error is x. When 100 observations are taken, random error becomes, that is x2 by x1 equal to n1 by n2. What is n1? Initially 10 and finally 100. This is 1 by 10 and x2 equal to x1 by 10, where x1 is x by 10 will be your answer. Simple. Okay. Now, next, propagation of errors. This is the final area of the error analysis. Propagation. Propagation means what? Suppose two quantities are measured, there is some error. When those two quantities are added, or subtracted, or multiplied, or divided, or any other operations. So in the case of operations, after doing the operation, what will happen to the individual errors? Whether those individual errors are propagated or updated or become addition or subtraction or multiplication or division, whether they are also operated according to the given operation or not, what will happen to the error? So that is about the propagation of errors. In propagation of errors, there might be addition or subtraction or multiplication or division. Remember, in addition or subtraction, absolute errors are added. In addition and subtraction, absolute errors are added. In multiplication and division, percentage errors or fraction errors are added. This is the working rule. So let us discuss about the addition and subtraction. Let me take two values here. Let us say given data is something like this. A value is given as A with absolute error and B with absolute error. And remember, question may be given in three ways. This question. One method is they will give you true value with absolute error. or sometimes the question may be given or numerical may be given in terms of the percentage errors, or the numerical may be given in terms of the least count instrument. They may mention something like this: yeah, this length is measured with screw gauge, this length is measured with vernier calipers, this is measured with millimeter calibrated scale or centimeter calibrated scale. Simple, they won't mention the error. So always remember, if they won't mention the error, just they give the instrument, that means least count will be error for that, maximum possible error. So that will be considered as the absolute error. And now, just now we had a discussion, right? In the case of addition or subtraction, which errors are added? Absolute errors are added, and the operation is the addition. So for addition operation, absolute errors must be added. That means delta A plus delta B, because addends are A and B, right? So A error is delta A, B error is delta B. Those two things must be added. So delta R is delta A plus delta B. This is the working rule. And final conclusion, we know that delta R equal to delta A plus delta B. In this case, first case, the given data is delta A, delta B, directly added. And the operation, main operation is A plus B, directly added. And in the case of this, how to handle? Percentage delta A into A divided by 100 will be your percentage delta, original true value divided by 100 will give you the delta A, delta B value. And after getting these two, you can get to this step. That is the actual working rule. Now, suppose if the least counts are given, simple, least count is itself is the absolute error, and after getting these two things, come here. It looks like a little bit clumsy, right? So let me again give you an idea with proper alignment. Now let us see. Now I am just modifying the structure. Given data will be in three formats. The first format will be in terms of the absolute error. And the working rule is R equal to A plus B, delta R equal to delta A plus delta B. And a given data may be given in different way in terms of the percentage error. Given data may be given in another way in terms of the least count. Simple. So here it is very easy. What is the working rule here? Delta A plus delta B. So for first kind of the data, I have delta A plus delta B readily available with me. So for this kind of the question, I can solve it directly. But for this, I need to process. I need to do one more step here to find out the delta A. What is delta A? Multiplication of the given values divided by 100. So A into percentage divided by 100. That will be my absolute error delta A. Same delta B equal to B into percentage delta B by 100. After getting delta A, delta B, take these values and substitute here. That is working rule. Suppose in this case, least count is given. Least count itself is delta A, I mean absolute error. So I can write delta A as LC1, delta B as LC2, and I can take these values and substitute here. So whichever the way of the given data, now I am ready. I know how to handle that. First data, direct substitute. Second method, just to process. Third method, this is also direct, and substitute here. And after this, I'll observe the options. So in the options, you may be given any of this way: R plus or minus delta R delta R by R, and percentage delta R equal to delta R by R into 100, R plus or minus percentage delta R. So whatever the way, you have to be process all these things. So the question may be representation of in terms of the absolute error, or fraction error, or percentage error, or representation in terms of the percentage error. So these are the four kinds of the numericals possible with these three different kinds of the given data. So three different given data with four possible questions, 3 into 4, 12 kinds of unique numericals for addition operation. For subtraction again, 12 kinds of the unique models. And let us see in the case of multiplication and division. So in the case of multiplication and division, please keep in mind, For multiplication, absolute errors are added or percentage errors are added. So in the case of multiplication, if the given data is this one, absolute, use the formula relative errors are added. That is delta R by R equal to delta A by A plus delta B by B. In the case of percentage error data, add percentage error directly. Add percentage error. Percentage error is directly percentage errors data addition. Percentage delta A plus percentage delta B. And from this, you can get the relative error. Or from this relative error, you can get the percentage error based on the question. Suppose if the given question is LC1 and LC2 or least count, follow the same method of the first one. We know that LC1 itself is the delta A or delta B. So now apply the working rule as percentage, fraction error is equal to sum of the fraction errors. So LC1 by A plus LC2 by B. And after this you can find out the percentage error. So first kind of the data you can find out the relative error or percentage error. Second kind of the data you can find out the percentage error or relative error. Third kind of the data you can find out the relative error as well as the percentage error. And from these, all these two, you can come to the original based on the options and questions. You can figure out whichever is possible. Again in this case also, multiplication and division, either fraction errors added or percentage errors added. So here for each operation, addition, subtraction, multiplication and division, you have 12 unique models and 4 operations, 48 kinds of the unique application questions are possible in terms of the numericals of the physics in error analysis. And this is how you should understand, this is how you should think, how the examiner will give you the numerical here. Now, let me come to the next part, or else once let us see division also. Division, given data will be in 3 ways again, and the operation is A by B, and the first case delta R by R equal to delta A by A plus delta B by B, and after finding out the fraction error I can get the percentage error. And in the second case, the given data is percentage error. So I will apply the rule percentage errors are added. After getting this, I can get the fraction error from this data just by division of the 100. And this one, these are all absolute errors. So first I will process the fraction error equal to sum of the fraction errors. And after getting fraction error or relative error, I can get the percentage error. So whichever the data is given, according to that, according to the question is being asked, you can process the things. Again, you will be getting 4 kinds of the questions. Yes. So as I told you already, you have 48 unique models in propagation of the errors for addition, subtraction, multiplication and division. I think you got the complete idea about propagation of the errors. And last part, we have propagation of the errors in the case of powers. Suppose if you have something, the format of the power is something like this: x is equal to k times a power n. What is a power n here? A is multiplied n times. It is same as the multiplication operation. In the multiplication, either relative error is added or percentage error is added. So I can get this one as delta x by x equal to n times delta a by a, or percentage delta x equal to n times percentage a. And the second way, if I have the same power but with more than one quantity involved, either multiplication or division. So here the rule is very simple: delta x by x equal to a power l. So l power times fraction error plus b power m power times base fraction error plus c power n are divided by c power n, so n times delta c by c, or else same percentage error. So this is the working rule for the power model. Now we are ready to discuss the problems. So this is problem solving session. And whatever the things we discussed till now, we must apply at the time of the problem solving. I told you already, problems are broadly divided into first category, statistics. A measurements, values, observations will be given, and 3 types of the errors are asked here. And second, propagation of the error, either addition or subtraction or multiplication or division, with 3 kinds of the data, with 4 kinds of the problems. So 3 into 4 12 into 4 operations 48 models. And power just now we discussed 2 models in power. So total 50 unique kinds of the problems models. Now let us see one by one. Problem solving approach, relative error or percentage error, you please be careful, there will be no dimension, no units. Okay, and errors never propagate in case of constants. So see here 4 by 3 pi are constants, so they never propagate, only r power 3 will be involved here. So here delta v by v, r power 3, so 3 into delta r by r. And problem solving strategy, first be careful evaluating error in the formula. How to approach? Approach 1. If you have powers, use the change into multiplication. Multiplication and division, change into addition. And approach 2. Approach to addition and subtraction, calculate absolute error first and then apply the rule. Suppose if you are given multiplication and division, then calculate relative error, percentage error, then approach to the absolute error. This is the basic approach, and already we discussed all these things. It is just an idea. When a problem is given, how to approach, either approach 1 or approach 2, right? Now there is a question for you. The percentage errors in quantities PQRS are given, and the relation between PQRS is also given, and errors are also given. The question is, what is maximum percentage error in the value of A? Always focus on the last part question only. Question is maximum percentage error, and given thing is power. It is very simple, power model and percentage, and given data also percentage. It is as simple as this. So delta A, percentage delta A can be written as P power 3, so 3 into percentage delta P, plus Q power 2, so 2 into percentage delta Q, plus square root of r power 1 by 2, so 1 by 2 times percentage error in r, and s power 1, so 1 into percentage error in s. So this is the idea, and after this just a simplification, substitution and simplification. What is percentage error in the P? 0.5 percentage, Q 1 percentage, R 3 percentage, S 1.5 percentage. Just to substitute the value here, 3 times 0.5, 2 times 1 by 2, 2 times 3, and 1.5. 1.5, 3 plus 2, 5 plus 1.5, it is 6.5, and your option is A. Yes, A is the right answer. I hope you got the things how to do. We can solve this within 1 minute. Now next question, the radius of the sphere is measured as 10 plus or minus 0.02 percentage, and the error in the measurement of its volume. For such kind of the questions, you must know the volume of the sphere formula. If you don't know that, you can't handle this. And given data, we have percentage errors. And once let us write the formula, V equal to 4 by 3 pi r cube. 4 by 3 constant, pi constant. It is power model. Propagation of error in the power. So r power 3. So percentage error in the volume equal to r power 3. 3 times percentage error in r. And what is percentage error in r? That is given as 0.02 percentage. So it is simple, 0.06 percentage. But the question is not percentage error. The question is absolute error. So for that, how to handle? Percentage error is delta V by V into 100, which is 0.06. And from this, you just find out the delta V. Now, delta V by V equal to 100 is taken that side, and it will become division. And delta V equal to 0.06 divided by 100. This V is coming this side and becoming multiplication into, what is V? 4 by 3 pi r cube, r value 10. So by simplifying this, I am going to get 8 by 10 times pi, and 8 into 3.14 by 10, I am going to get 2.512, which is this one, 2.51 cc. Now let us discuss about a question from JEE Mean 2015. Here, this question, first observe what is the given data here. L is given 20.0 centimeters, and as well as 1 mm accuracy, that is delta L. And you must convert this into the same units of the original one, centimeters. It is 1 mm, you must convert to the centimeters, so 0.1 centimeter. Now 90 seconds, that is t, as well as the 1 second resolution, that is delta t. So all the things are given. The question is accuracy in the determination of the G, which is, as per the options we can understand, it is percentage error in G. Now, what is the expression given? 2 pi square root of L by G. From this, square on both sides, you will be getting t square. 2 pi square is 4 pi square L by G. And we want G as a subject, so G taken to the left hand side and t square is taken to the right hand side. 4 pi square L by t square. Here 4 constant, pi constant. And the here propagation of error, the quantities involved L and T only. And given data, we have L with us and T with us. So we know that the percentage error in G or fraction error in G can be written as, according to this, L power 1. So 1 into delta L by L plus T power 2. So 2 into delta T by T. And we have all the values with us. Delta G by G equal delta L value, how much? 0.1 centimeters. And L value, how much? 20 centimeters. And delta T value is 1 second. And T value is 90. Just simplification of this one, 1 by 200 and 2 by 90. And here percentage of error means this fraction error into 100. So here percentage delta G can be written as 1 by 200 plus 2 by 90 times 100. If you take 100 inside, what are you going to get here? 100 by 200, 0.2. Yes, plus 200 by 90. So you are going to get this one as 1 by 2 plus 20 by 9. And with proper simplification, I can write this one as 18 plus 2. So 2 plus 2 by 9. And the simplification of this one can be 0.5 plus 2 plus it is 0.22. I can get 2.72 approximately. Yes. So this is my percentage error in the G. And after even rounding off, I will be getting 3% approximately. Yes. So next question. And it is from JEE Main 2016. A student measured the time period of 100 oscillations with given values 90 seconds, 91 seconds, 95 seconds, 92 seconds. If the minimum division in the measuring clock is 1 second, what does it mean? It is least count and it is error. Okay, maximum possible error. Now, what is the question here? Reported mean time should be measured. So true value is not given here. So take the average. 90 seconds, 91, 95, 92, average of this one. And it is 368 by 4, it is 92. So let us see of the options. So all the options are 92 true value. But the question here is, what is absolute error? So to find out the absolute error, we need to go for the individual absolute error and mean absolute error. So individual absolute error, true value I know, measured value I know. So the difference between 92 and 92, the difference between 92 and 91 is 1, difference between 92 and 95 is 3, difference between 92 and 92 is 0. So after all these, the mean absolute error is 1.5. So after getting 1.5, here I need to take the rounding off here. So to get this one single significant error, so I will be getting 2. And this will be finally, because here 5 is preceding digit, 5 is 1, 1 is odd number, 5 is followed by nothing, so PD becomes PD plus 1. Yes, so that is why 2. So 92 plus or minus 2, and the answer is option A. This much simple. Next question from 2017. Let us observe the following observations were taken with D value and H value and G value. And expression also given, you are lucky. T equal to RH by 2 into 10 power 3 Newton per meter. But be careful, the given data we have the diameter, but the expression contains radius. And here you must be very careful to get the R, express the expression in terms of the diameter you should write. Don't get the value R from here. So by that way, you should handle RHG by T can be written as DHG by 4. D value we know already, H value we know already. And it is just a division operation or power operation you can handle. So delta T by T equal to delta D by D plus delta H by H, and G can be considered here as constant. So from this area, by substituting delta D value and D value, delta H value and H value, and with proper simplification, I am going to get percentage error as 0.80 plus 0.68, 1.48 percentage. After rounding off, I can get this as 8 is the DTR greater than 5, PD will become PD plus 1, that is 1.5 percentage, which is B. So this is the way we handle even JEE main questions also can be solved within 1 minute. So my dear students, I hope you understood this one. And one more question from JEE main 2018. The density of a material, the shape of a cube is determined by measuring 3 sides of the cube and its mass. If the relative errors in measuring the mass and length are respectively 1.5 percentage and 1 percentage, the maximum error in the determining the density. Density is basically mass by volume, right? So the given quantities are mass error is given and length error is given. It is a cube. Cube volume is L cube. I mean L power 3, side power 3. So from this I can get delta percentage error in the density is m power 1, so 1 into delta percentage error in m, and L power 3, so 3 times percentage error in the length. As the given data is directly in the percentages, I am directly going for the percentage formula. If it is absolute, I would have gone to the relative error formula. And just by substituting 1.5 plus 3, I will be getting 4.5 percentage, which is option C. So my dear students, I hope you understood this. Numerical also we can solve within 1 minute. And this is how we solve the numericals, and error analysis is completed. Still, if you have any queries, you can contact us through doubt solving window. And if you have any constructive feedback or any queries, you can get back to us with WhatsApp number or mail ID or even the chat box. Thank you all.